Good afternoon and welcome to today's webinar on evaluating nuclear waste and safety considerations for advanced nuclear deployment. We'd like to thank the DOE Office of Nuclear Energy for their support of today's webinar. Before we dive in, I want to take a couple of minutes to acknowledge some housekeeping notes. First of all, please enter any questions into the Q&A box at any time during the webinar, and we will get through as many questions as possible following the presentations. This webinar will be recorded, and the presentations in the recording link will be shared with webinar registrants after the webinar. With that, I'd like to introduce our moderator for today's discussion, Commissioner Bobby Janecka. Commissioner Janecka has served as one of 3 appointed commissioners responsible for oversight of the state environmental agency, the Texas Commission on Environmental Quality, or TCEQ. His work focuses on leading the TCEQ Border Initiative, serving as the state liaison officer for Texas with the U.S. Nuclear Regulatory Commission, and representing the agency as a member of the Texas Energy Reliability Council. He also serves as a member of the U.S. Environmental Protection Agency's Governmental Advisory Committee, representing the interests of the TCEQ to provide advice to the EPA administrator on a broad range of issues. His previous experience includes roles in the Office of the Governor, the Texas House of Representatives, and the Texas Comptroller of Public Accounts. He is a graduate of the Texas A&M Bush School of Government and Public Service, the University of Texas at Dallas, and the Governor Executive Development Program at the University of Texas LBJ School of Public Affairs. At this time, I will pass things over to our moderator, Commissioner Janecka. Welcome.
Thank you. Thank you very much, Catherine. And I want to welcome everyone on behalf of the NARUC-NASCIO Advanced Nuclear State Collaborative. Thank you for joining today's webinar on evaluating nuclear waste and safety considerations for advanced nuclear deployment. Today's webinar topic is part of a larger series of webinars that the Advanced Nuclear State Collaborative has been exploring over the past year. The ANSC convenes state utility regulators and state energy officials to enhance collective understanding of the unique regulatory and policy questions surrounding the consideration and deployment of new nuclear generation and supports peer learning across states. Today, we are welcoming experts to share more with us about characteristics of spent fuel produced by advanced reactors, prospects for reprocessing advanced reactor fuels, and the Nuclear Regulatory Commission's new SMR Emergency Planning Zone rule. This is a topic of great interest to me in my work at the Texas Commission on Environmental Quality. And to answer the question for all of you, why am I not a nuclear or a regulator, a state regulatory agency? Why am I here? I'm grateful to be here for TCEQ. And I represent part of the agreement state authority held by the Nuclear Regulatory Commission, granted to the state of Texas. We oversee the uranium mining recovery operations in the state. We oversee the waste and processing of radioactive materials after it's ceased to be useful. And they've included licensing of the state disposal facility, the Texas Compact Waste Facility in Andrews County, that many of you are familiar with in some way, shape, or form. It's the first the low-level facility sited and constructed since Congress acted and took action in 1985 for the Little Waste Policy Act, inviting compacts to create compact sites. Let me briefly turn now and introduce our speakers for today in the order that they will be presenting. Catherine Wise is a program officer with the Board on Energy and Environmental Systems at the National Academies of Science, Engineering, and Medicine. In this role, she facilitates consensus studies by expert committees that provide evidence-based scientific advice to the federal government and other stakeholder organizations on issues of energy policy. Her current and prior work has supported a wide range of energy topics, including advanced nuclear fuel cycles and reactors, and fusion energy, to name a few. Prior to the academies, Catherine worked as a graduate research assistant studying proton-coupled electron transfer and electrochemical systems. She received a BS in chemistry from the College of William & Mary and a PhD in inorganic chemistry from Yale University. Next, we will hear from Dr. Robert Ledoux, who currently serves as a program director at the Advanced Research Projects Agency, Energy, aka ARPA-E. He is the program director of the ARPA-E Onwards program, which aims to reduce the disposal impact of advanced reactor waste. Prior to joining ARPA-E, Dr. Ledoux served as the founder, president, and CEO of Passport Systems, a technology company in non-intrusive cargo inspection, Prior to founding Passport Systems, he served as vice president of Pyramid Technical Consultants, developing hardware and software for the control of magnetic scanning systems and accelerator control used in semiconductor manufacturing equipment, and as an associate professor of physics at the Massachusetts Institute of Technology, where he studied high-energy nuclear interactions in search of new phases of hadronic matter. Finally, we'll hear from Jon-Michael Murray, who is Clean Air Task Force's Nuclear Policy Manager. Jon-Michael joined CATF from the U.S. Department of Energy's Office of International Affairs, where he was a policy fellow working on international climate and clean energy engagement. Prior to his time at the DOE, Jon-Michael worked to promote U.S. trade and export competitiveness at the International Trade Association. Previously, Jon-Michael explored entrepreneurship and worked in the private sector in Thailand after finishing his service as a nuclear operator in the U.S. Navy, where he was stationed on an aircraft carrier out of Japan. He received a master's in international public policy from Johns Hopkins University, a master's in environmental management from Yale University, and a BS in nuclear engineering technology from Thomas Edison State University. At this time, I would like to invite Dr. Catherine Wise to begin her presentation.
Thank you very much. Good afternoon, everyone. Thanks for inviting me to speak today about the National Academy's report on merits and viability of different nuclear fuel cycles and technology options and the waste aspects of advanced nuclear reactors. As mentioned, my name is Catherine Wise, and I was one of the National Academy staff members leading this study, which was chaired by Janice Dunley, with Patricia Baisden as the vice chair. Next slide, please. So as you're all likely aware, in recent years, the US Congress, Department of Energy, and private sector have expressed considerable interest in developing and deploying advanced nuclear reactors and their associated fuel cycles, which have several proposed advantages over the existing fleet, including improvements in economic competitiveness, reductions in environmental impact, and enhancements in nuclear safety and proliferation resistance. So this National Academy study, which investigates some of these proposed advantages, was undertaken in response to congressional mandates in the Consolidated Appropriations Acts of fiscal years 2020 and 2021, and it was sponsored by the Department of Energy's Office of Nuclear Energy. Next slide, please. So I'm showing here a paraphrased version of the study statement of task that highlights the three main components of the study. First, to assess the merits and viability of different nuclear fuel cycles, including those that may involve reprocessing for both existing and advanced reactors. Second, to examine non-proliferation implications and security risks of advanced fuel cycles. And third, to understand the waste management and disposal options for various proposed advanced reactors. And it's this third point that I'll be focusing my remarks on today. Next slide, please. On this slide, I wanted to just highlight and recognize the very distinguished group of experts that we had on this committee to respond to the statement of task. These are the individuals who are responsible for developing the content, findings, and recommendations that I will be sharing with you all today. Next slide, please. So to be able to really understand some of the merits and viabilities of different advanced reactors, the committee first wanted to take a look at the current status of fuel cycles and reactors in the United States. So thinking about where are we now as a starting point and a baseline. And here I'm showing a schematic of the current once-through fuel cycle with light water reactors and low-enriched uranium fuel that highlights with light and dark gray shading which components of the fuel cycle we have partial or no domestic capacity, respectively. And the committee found that this existing baseline fuel cycle has several merits, including that it's less expensive than fuel cycles involving recycling, that it has a currently reliable international nuclear fuel market with multiple suppliers, that it's compatible with projected available uranium resources, and has well understood proliferation resistance, both of the spent fuel and the entire fuel cycle. And additionally, importantly for thinking about waste management, the light water reactor spent fuel is reasonably consistent and uniform across the entire fleet. Next slide, please. All right, then moving to advanced reactors, I'm showing here sort of the vast array of different reactor designs that the committee looked into. So the different design classes are shown across the top of the table, and their various sort of design characteristics and some fuel cycle requirements are shown. And really what I wanted to highlight on this slide is the proposed fuel cycle for most of these advanced reactor designs is the once-through fuel cycle. And next slide, please. So just to summarize some of the important observations from that table on the previous slide, there is a wide range of advanced reactor designs being proposed that have various coolants, fuel types, fuel forms, fuel enrichment, and neutron spectrum initiating fission reaction. But most advanced reactor developers are opting to use the once-through fuel cycle initially, though some plan a possibility of closing either partially or fully their fuel cycle in the distant future. But should these reactors be commercially deployed, the resulting spent fuel and associated waste streams will vary considerably from the current standard spent light water reactor low enriched uranium oxide fuel assemblies. Next slide, please. So that then begs the question, what type of waste will these advanced reactors generate? Because they plan to use fuels with higher enrichment and or burnup, as well as new types of fuel materials and designs, the resulting spent fuel may differ in amount, chemical composition, radionuclide inventory, thermal power of fuel assemblies, and durability of the fuel in a disposal environment compared to uranium oxide spent fuel. And additionally, most of these advanced reactors would generate additional waste streams for which there's little experience or mature technical ability to manage, and which would entail additional costs not encountered in managing and disposing of light water reactor spent fuel. Some examples of this include the spent TRISO fuel, large volumes of spent TRISO fuel from high temperature gas reactors, radioactive dust from pebble bed reactors, irradiated sodium waste and sodium bonded spent fuel from sodium cooled fast reactors, radioactive off gases and spent fuel salt waste from molten salt reactors, and the large quantities of irradiated graphite waste from the moderators or reflectors of several different advanced reactor designs. Next slide, please. When the committee was starting out, it heard from some of the congressional staff members who had worked on the mandates for this study, and they asked the committee to consider this question of whether advanced reactors could, quote, solve the waste problem. And the committee really took that to heart, and several of the findings, which I'm showing excerpts here on the slide, tried to address components of that question. So first, the committee noted that without a final geologic disposal strategy, expanding nuclear power with advanced reactors will just add to the amount of spent fuel and associated waste requiring disposal, and would increase the complexity of that challenge because of the new types of fuels and waste streams that would need to be disposed of. Additionally, any reprocessing or recycling of spent nuclear fuel would introduce more safety and environmental considerations over the management of the current baseline fuel cycle. And then while it's theoretically possible to do, reducing the 86,000 tons of legacy spent fuel using advanced reactors is really not practicable to achieve in the near future. And finally, even a fully closed fuel cycle with recycle and transmutation operated over decades will still require a geologic repository for the disposal of fission products. Next slide, please. So how then did the committee recommend moving forward on nuclear waste disposal? First and foremost, they recommended that Congress should establish a single mission entity that would be responsible for cradle-to-grave management and disposal of nuclear wastes. So from the discharge of the waste at the reactor plant to its final disposal in the repository. And this recommendation is not new. They were echoing prior recommendations from other study committees along the same lines. They also recommended that the immediate future focus of the U.S. nuclear waste management and disposal program should be to plan for geologic disposal of existing spent nuclear fuel, but also to prepare for deployment of advanced reactors. The Department of Energy, Nuclear Regulatory Commission, and Environmental Protection Agency should develop regulations and standards for a generic repository and new types of spent fuel and waste forms to support geologic disposal of advanced reactor fuel types. And at the same time, advanced reactor developers should anticipate the impact of new fuel types on their performance in a geologic repository. Next slide, please. So what I've shared very quickly today is just a subset of the committee's findings and recommendations. As I mentioned, the report also covered aspects of the front end of the fuel cycle, as well as non-proliferation considerations for advanced fuel cycles. But I did want to leave you all with just some overarching conclusions from the report. So first, the vast array of advanced reactor and fuel cycle concepts, if realized, would significantly diversify reactor and fuel cycle technologies used in the United States. And trade-offs are necessary when assessing the potential merits and viability of these different reactors and their associated fuel cycles, because not one single advanced technology can concurrently provide for all the potential benefits relevant to the scope of this study. And therefore, the US government and industry going forward will have to decide which features or attributes of advanced reactors and fuel cycles best align with US energy needs without increasing proliferation risks, having an adverse impact on the environment, or imposing an unacceptable economic burden on current and future generations. Next slide, please. Thank you very much for your attention. I'm showing here the link where you can download the full report if you're interested, and I'll be happy to take any questions during the Q&A period later on.
Thank you, Dr. Wise. I'll remind the audience you may submit questions through the question and answer feature of the Zoom conversation, and we're running through the final additional addendum slides that Dr. Wise included with further details. We're now going to move on to Dr. Robert Ledoux with his presentation. Thank you.
Well, thank you very much for this opportunity to speak to you about ARPA-E's programs and advanced reactor fuel cycle portfolio. And I also want to thank Catherine for that beautiful overview. Saved me a lot of slides, giving the full context of what these advanced reactor fuel cycles look like and what are really both the opportunities and the challenges of these advanced reactor fuel cycles. Next slide. And of course, I want to thank all my wonderful colleagues at ARPA-E. This is the full fission team. In particular, single out my co-program directors, Dr. Jennifer Schaefer and Dr. Bill Horak, whose work I'm also going to be discussing here. Next slide. So just 1 minute background of ARPA-E. What some people don't know, what is ARPA-E? Well, ARPA-E is part of the Department of Energy, and it is devoted to doing high-risk, high-impact work, just R&D in the energy field. And it has 5 basic tenets of its charter, and they are to reduce inputs, improve efficiency, reduce emissions, improve radioactive waste management, improve energy infrastructure resiliency. I think we can all agree that nuclear fission and power is crucial to every one of these, and in particular for mitigating climate change. We believe it forms an essential part of our portfolio of R&D. Next slide. So Catherine really highlighted all the different fuel cycles coming out, all the issues associated with them, and so on. So ARPA-E's, this is its full fission portfolio, and originally we started not that long ago, really focusing on advanced reactors. Initially, CapEx, how to reduce the cost of building them, right? They're not cost effective, they won't be built, and also improving their OpEx, their operational expenses. And those were our first 2 programs. When we looked at the landscape recently, we really realized that if advanced reactors are going to be deployed, we need to address many of those challenges that Catherine pointed out, the National Academy of Science had pointed out. So we really dug down into what is the R&D needed to really provide stakeholders with the information of what options could be to address this issue. And the first program was Onwards, which I stood up in 2021, is focused explicitly and completely on just advanced reactor waste. And I'll discuss this in more detail, but the aim of it is to try to minimize the impact of advanced reactor waste. And that was followed by my colleague Jen Schaefer's program, Curie, which explicitly looks at, can we basically recycle the existing light water fuel, spent nuclear fuel, in a cost-effective way, satisfying all those challenges that were highlighted by Catherine. And then the way we do them, we're looking at really going the next step after that, transmutation. We heard that even if you deal with all the uranium and the transuranics, you still have the fission products. Well, can we transmute that last long-lived fission products and really try to tremendously mitigate the time required for geological repository? And we're also working on other uses of nuclear power other than just electricity production, but also, for example, industrial heat and so on. So that's the full portfolio. But of course, for this meeting, I'm just going to concentrate on Onwards and Curie to give you a feeling for what kind of R&D is ongoing and how it tries to address those issues that are associated with it. Next slide. So first of all, what is the time scale of all of this? And this is just a notional time scale. I've already discussed that in the blue above. We really have been focusing at ARPA-E on the digitization, for example, to reduce operational costs, recycling of spent nuclear fuel, and waste disposal of all forms. But to give you a time perspective, I mean, these new reactors, many of them with new fuel cycles, will be coming on air in the not too distant future. So we do have a lot of very important R&D issues that need to be resolved to inform any type of deployment we have of advanced reactors. Next slide. So the Onwards program, just to be specific of its goal, its goal was to develop technologies significantly minimize the disposal impact of nuclear waste from advanced reactors, and trying to do that in some cost range, which is economical, which was like the nuclear waste fee, which is something that was imposed until relatively recently. And so if we can do that, what are the goals, the stretch goals? ARPA-E likes difficult problems, but if we could attain them, would make a tremendous difference. And the first was to try to significantly reduce the waste volume. I'm talking only here about high level waste, of waste volumes or a positive footprint. Always keeping in mind that we must do the safeguards along with this, and we have very different fuel types, so it's not counting fuel pins. There may be both reprocessing of both fuels, and so we have to be sure we can do the mass accountancy. Also, depending on the waste stream or even the used nuclear fuel, we very likely will need some new waste forms that can achieve these goals of reducing the waste volume. Next slide. Curie is focused on taking the existing light water reactor, used nuclear fuel, and trying to see if that can be reprocessed and recycled into new fuel stocks for advanced reactors. And of course, to this to be viable, it would have to be done at an economically reasonable way, both in the reprocessing and as well as the cost of the new fuel stock. So this is very heavily focused also on the economics of what recycling might look like. Next slide. So rather than go through all our projects, I think that I'll just try to give an illustrative example which tries to connect all the dots, both in the issues at hand here, as well as our portfolio. So I start with a company called Oklo, which we fund under the Onwards program, actually in the Curie program too. And what this strings together is, although it's focused on trying to do the R&D for a new form of recycling called pyroprocessing, which has been used actually on EBR-2 fuel, but basically has not been really commercialized. And so here the stream is looking at every piece of that puzzle, the basic reprocessing that would have to be done. Can that be recycled into new fuel stock back into the fast reactor? And then it will have a waste stream. And what are the options of trying to make that path to the repository economical, either in what the waste forms are, the volume of them, the transport, and even considering an alternative to a mined repository, a deep geological repository. So it kind of strings together all the pieces of that. Next slide. From the Curie program, I just want to show you that to make it both economical and to satisfy non-proliferation concerns, we really want to do R&D into in situ, in-process identification of fissile material. And so this is just one of the detectors that's being worked on in Curie, which basically has really exquisite isotopic separations. And if this could be done during process, it would both improve the processing potentially in economics, as well as satisfying some of the mass accountancy, which is required also. Next slide. And then finally, we may need just new waste forms from molten salt reactor, whether once through or even if it's any form of recycling or reprocessing to get into the repository. Can we develop much better waste forms? And much better means both much higher loading, reduces the volume in the repository, and better durability and cost to produce. So here's one example which is fascinating, because actually it's being led by an informatics company doing machine learning and informatics on chemistry, basically, to try to rapidly evolve waste forms to meet our needs and to rapidly test them. So this may be an essential part of whether it's once through or it is some form of recycling. Next slide. And finally, we have to look at this as a whole system. And a lot of the economics and a lot of the safety is really determined by the handling, whether it's once through to the repository, whether it's recycling, waste form, interim storage, repository. Can we come up with in this case, a universal canister that can handle every waste form from all the advanced reactor fuel cycles and be able to be used in any form of interim storage or geological repository? Once again, trying to consider the full system impact of advanced reactor fuel cycles. And that's it for this overview. I'd just like to say from ARPA-E, next slide, from ARPA-E, of course, we always say, our model, if it works, will it matter? We do this to fundamentally try to get something out there that can actually be used. And next slide, I'll just end with, we're going to have a question and answer here, but of course, we're always open to further questions directly at ARPA-E. And any of these programs, if you just Google them on, you will find the details of the projects within them. So thank you for your attention, and I look forward to questions afterwards.
Thank you, Dr. Ledoux. I have a quick question to follow up on one of the topics that was offered in the panel. I know we said we'd have questions at the end. I'll ask it now, and you can start thinking about it. Is there a back of the envelope calculation for existing spent fuel inventory for reprocessing? What does that roughly translate to into additional fuel supply, fuel stocks, and what does that mean for our potential fuel recycling communities? I think there's a little math there. So I'll ask the question, and now we turn to our third and final panelist. We're doing good on time. We're a few minutes ahead, three minutes ahead, I think. Dr. Jon-Michael Murray now with your presentation. Thank you. And you're muted, sorry.
Thank you, Commissioner Janecka. All right, this topic of emergency planning zones and SMRs and advanced reactors is not the most exciting topic, so I'll apologize in advance, but if we can get through to the end without anyone falling asleep, I think we will have achieved something. So next slide, please. All right, so quickly the objective and the agenda. So the purpose of this presentation is to help the audience understand the concept of emergency planning zones and why they're significant for nuclear regulation in the United States, as well as to understand the implications of the NRC's new EPZ ruling that will be finalized this year. So first, to do that, I'm going to detail some of the background on my organization quickly, then talk about what an EPZ is, then detail the background of EPZs and how we arrived at the current regulations, and then finally turn to the new EPZ ruling and the key changes it makes. Next slide, please. All right, now to the Clean Air Task Force, my organization. We are an environmental nonprofit focused on pragmatic climate solutions. We've been around since around 1986. Staff almost at 200 now from 2 years ago, where we actually had about 25 to 30 people. So we've had a lot of growth, and we have offices around the world, based in Boston, but also in DC and Brussels. And we take the vast majority of our funding from philanthropic donors. Next slide, please. Now, I am a part of the CATF nuclear team, and we believe that the evidence shows that nuclear energy is essential to meeting our decarbonization goals, as well as meeting future energy demands, future growing energy demands, especially in the developing world. However, as you can see on the bottom right here, nuclear deployments have stalled over the last several years, decades. But what we think is that we need to see nuclear deployments grow from where they are now globally at around 10 gigawatts per year to hundreds of gigawatts per year. And as you can see in that top right graphic, we think that can happen over several different types of applications, especially for advanced reactors. So our mission is to try to catalyze the commercial and policy conditions for the nuclear energy to scale at this level to meet our climate objectives. So next slide, please. This is our nuclear theory of change at the Clean Air Task Force. And what we have done is to divide the nuclear ecosystem into the three primary pillars of social, political, technical, and markets. And within each of these pillars, there are several different nodes where we think there are opportunities for transformative change. And what we do is we survey this map, and depending on our expertise and capabilities and what's being done already, we find places to act. Next slide, please. All right, now to the emergency planning zones. So what is an emergency planning zone? It's a designated area, and I'll just read this slide directly. It's a designated area around a nuclear reactor where specific emergency preparedness measures are in place to protect health and safety from radiological emergencies. Now, I want to underline that last part, radiological emergencies. This is not to protect from nuclear explosions. That's impossible at a nuclear power plant. So next slide, please. One other disclaimer on this slide is that these measures are a precaution. Out of an abundance of caution, nuclear plants are very safe, and there's actually a lot of evidence to suggest that the current standards may be far too stringent. But next slide, please. All right, so some background on these emergency planning zones. They were first conceived in a report published by the NRC and the EPA in 1978. And what this report did is it looked at potential accident scenarios in terms of the radius of radiological contamination in a worst case accident. And depending on that, assigned what would be ideal radii around the plant for emergency preparedness measures. And it specifically identified 10 and 50 miles as the meaningful areas. So after additional proceedings and some new considerations after the 3 Mile Island nuclear accident in 1979, the NRC finally codified the 10 and 50 mile EPZs in a rulemaking in 1980. However, within that new regulation, there was a provision that allowed for exemptions on a case-by-case basis, specifically for reactors that had a power rating of less than 250 megawatts thermal or gas-cooled reactors. And you might recall that NuScale in 2022 had a methodology approved by the NRC to determine its EPZ in a different way than the prescribed 10 to 50 mile EPZs. And the reason they were able to do that was by going through this provision for exemptions. So as a result of all of these new regulations, each commercial nuclear power plant is required to have on-site and off-site emergency plans to ensure public safety in the event of a radiological emergency. And within that area, it includes several different measures that require things like running drills with local safety officials and so on. And this is mainly overseen by the FEMA and NRC, but overall responsibility lies with the NRC. Next slide, please. All right, so there are two types of EPZs identified within the regulations. As I mentioned, 10 and 50 miles. So if you look at the graphic on the right, you can see a depiction of this, a radius around the nuclear plant where the nuclear plume is expected to have an impact, but it depends on various different factors. So that first EPZ at the 10-mile radius, which we call the plume exposure pathway, this is the area of greatest concern in the event of a very unlikely accident. And this is where evacuation is required, or if evacuation is not possible, then sheltering in place. And the secondary EPZ, which goes out to 50 miles, is of lower concern based off of harm that could potentially people could be exposed to based off of the radiological contamination. And in this area, evacuation is not required, but it could be in some specific scenarios. Mainly, we're focused on managing food and water contamination in these areas in the event of an accident, just to make sure no one eats or drinks anything that's been contaminated. Next slide, please. All right, and again, I'll read this one directly. This is the impetus for the new regulations that are being promulgated this year. So the existing regulations and guidance focus on large light water reactors. This is the regulation that was the type of technology that has predominated and was predominant during the time of the promulgation of this rule. And so recognizing the requirements were important for reducing regulatory uncertainty and for reactor licensing and enhancing the business case for SMRs and advanced reactor developers, especially with the potential opportunity to reduce the size of the EPZs. The NRC ordered a new rulemaking in 2016. So next slide, please. So some notes about this new rulemaking. It was actually proposed in 2020 and finalized, sent to the commissioners in 2022. But finally, just last month, August, the NRC released an announcement saying that the commission had committed to voting and finalizing the rule by the end of this year. So under this new rule, the facilities covered will be it's specific to SMRs, so not those large light water reactors. This is in the rule. It's defined as reactors less than 1,000 megawatts thermal, or also advanced reactors, so those non-light water reactors that might have different coolants and different fuels, but also for research and test reactors and medical radioisotope facilities. This rule will also apply risk-informed, performance-based measures. So this is to accommodate the new capabilities, new technologies, new safety features of small and advanced reactors. Next slide, please. So I want to make a note here also, as I mentioned at the beginning, that rule was finalized in 2022 and only just got committed to be finalized by the NRC last month. And it actually required the urging of various stakeholders, including the Clean Air Task Force. We, along with some partners, sent a letter urging the NRC to finalize that ruling. So this just kind of points to some of the inefficiencies within the current regulatory model and some of the things we need to improve. So next slide, please. All right, so what are the key changes of this new rule? Well, first, as I mentioned, it's focused on performance-based preparedness measures. So rather than being prescriptive, it is outcome-based. It identifies an outcome and allows applicants to make a case for how their technology can meet that outcome based off various different factors, rather than being site-specific and requiring specific standards like the current structure, which is very deterministic, and again is focused on large light water reactors whose risks are pretty well understood at this point. However, because SMRs and new technologies, as I mentioned, use a wide range of designs and safety features, this performance-based approach is really more appropriate and can reduce the administrative burden that would be required by the NRC to evaluate all the different exemptions that would be required under the existing rule. So this final rule provides a scalable approach to determining the size of the emergency planning zone. So again, the NRC provides a required outcome, and the applicants can try to meet that in various different ways based off of various different factors, some of which you see here, see listed here. And this provides an opportunity, if they can make the case for it, to reduce the size of their boundary to possibly the perimeter of their site, which we call a site boundary EPZ. So next slide, please. All right, and this new framework will also require that applicants demonstrate effective responses via drills and exercises. However, if the facility can achieve that site boundary EPZ, then they won't need to involve local responders in all the drills and exercises that are currently required. So this could be a big cost driver, as well as open up new business cases. And on that last point, the emergency preparedness requirements if satisfied, would also satisfy the requirements for co-locating independent spent fuel storage, because spent fuel is currently stored at all the reactors across the United States. Next slide, please. All right. So to summarize, emergency planning zones are important emergency preparedness measures meant to protect health and public safety. Now, they can be overly stringent, and the current regulations are not suited for the newest generation of reactors. But these updated emergency planning regulations in the NRC's new rule will allow for more flexibility while fostering predictability for how the NRC can evaluate emergency plans. And again, if the applicants can achieve those site boundary EPZs, it could significantly reduce the burden on those facilities in terms of drills and exercises. And they will also allow SMRs and advanced reactors to open up to new applications, like providing industrial process heat, like the project we see in Texas, actually, Commissioner Janecka, at Seadrift with Dow and X Energy. And next slide, please. That concludes my presentation. Thank you. Happy to take any questions.
Thank you. I will prod everyone in the audience to put your question hats on, and feel free to enter them into the question and answer box. Don't know that the raise hand function will work or be the swiftest way to do it, but I have a question to start us off with, to turn back to the start of our panel. I will invite Catherine, Dr. Wise. Could you comment a little, what were the committee's views on fuel cycles involving reprocessing and recycling of spent fuel?
Yeah, happy to. Thanks. So I'll, I guess, make a few points along these lines. So the committee did recommend that the current policy of the once-through fuel cycle with direct disposal in a geologic repository should continue for the foreseeable future, for many of those reasons that I shared on my slide about cost and well understood proliferation resistance and reliable markets and supply chains and things like that. They noted also that introducing mono recycling fuel cycle, like what is done in France, would just add costs to nuclear power generation, but have no significant benefits given the projected abundant uranium supply and at a low cost for the foreseeable future. However, they did recommend that the DOE continue to do research and development on advanced separations and transmutation technologies that could close the fuel cycle, just to not preclude that as being an option in the future. So sort of summary, they recommended to keep going with the once-through fuel cycle, but keep doing R&D at the same time.
I appreciate that. I think that tees up the question that I turned to Dr. Ledoux earlier, and I will turn now to him and reiterate that question.
Yeah.
How long could we power our nuclear fleet using only the used fuel available to us today without further?
So there's a simple answer to that, I believe, and any of my colleagues online can check. And there's one that the devil's in the detail. The simple one is most of the spent nuclear fuel is uranium. Right? So the bulk and 95% of the spent nuclear fuel is uranium. So all that 86,000 metric tons, right, is mostly uranium. So I guess I would answer it this way. If you took back all that uranium, you wouldn't have to mine uranium for, well, you can see it's 95% of there for all those gigawatt hours. So basically, I think the simplest way to look at it, it's just a source of, I don't know, hundreds of years of uranium without mining it. If you could separate it and use it as is, right? For recovering the fissile thing, I'd be very careful, because in all of ARPA-E's program, we will not support any R&D into a pure fissile stream, which means you either have to co-deposit all the transuranics and the uranium, etc. The point is there that that's probably only useful for a fast reactor. And if fast reactors go to higher fissile content, the devil's in the detail. So I think the simplest way to look at it is, for the uranium recovery, there's just a tremendous amount already there. And so that's the biggest benefit. for the fast reactors that want to close their fuel cycle, it could be a tremendous economic advantage because basically they could recycle all the transuranics. So I hope that answers your question. I think that's the big picture.
I think it does. I appreciate it. And I trust we're already getting some follow-up questions. So I think we'll circle back around if the audience has something else they still want to know on that front. And let me turn to Jon-Michael Murray with a very simple and blunt question. Does the new EPZ rule, as it's currently drafted and presented, does it mean that all small modular reactors can achieve site boundary EPZ?
Yeah, that's a very good question. Thank you. No, it does not, is the short answer. An applicant has to make the case based off of the various different factors and related to the specific design and the site that it should be allowed a site EPZ. It's very likely that many will, given their inherent safety features. NuScale was even able to do it through the current exemption process, but it is not guaranteed for any reactor.
Thank you. I have a question specifically for Dr. Robert Ledoux now in the chat from a colleague of mine from the state perspective on this problem from Jeff Szymanczyk. Given that heat loading is generally the most limiting concern for high level radioactive waste, why the focus on reducing volume of waste forms? Is the same heat load and smaller package is not necessarily not going to reduce repository size?
Yeah, so that's a great question. So the question could be what limits the heat load in a repository? So one partial answer to that is that's why we're also interested in deep boreholes, because in that case, it may not be important, the heat loading itself. Basically, if you get it down, then maybe the heat loading itself is not important. Also for the waste ones with 10x reduction, for things like the molten salt reactors and so on, it's a question about what's in the waste and what do you separate out. So like, if you separate out the uranium, but you still have the salts and so on, right? You do want to have a high loading of that waste, and it may or may not be that hot. So it's a fantastic question. You do lose something because of the heat, but you can also cool it in interim storage longer. So it's a multi-parameter space. But the way we looked at it is, let's get waste forms with high loading that you can go to high density to, and consider those other options. And if intrinsically, like you remove all the uranium, then basically it's just the intrinsic volume is that much shorter. So like only 1/30 of it, if you took out all the uranium, only 1/30 is waste, right? So even if the heat loading tripled that, you're still down to the 10x, right? So I agree, there's many details there, but we're trying to get the limit of the waste form, and then we can look at all those other effects, which are important.
I think I appreciate the complexity there. And we turn to a more general question. It feels somewhat political to me, and I don't know if there's a particular one of you that would want to answer, but if you have a strong answer, please, I'd invite you to lean in on this one. From an anonymous attendee, can we achieve climate change emissions targets without recycling nuclear fuel?
I'm not going to. Yeah, go ahead. Go. Yeah.
Climate change emissions targets without recycling. Absolutely. Yes. The recycling nature of I assume, reading into this question, I'm assuming that they are thinking about the emissions related to mining activities.
Got it.
And I think that can be solved by innovating on our zero carbon fuels, our alternative fuels, as well as there's another number of technologies, nuclear technologies that could contribute to this, and others. Maybe also EVs will help, although it's very different for a heavy industry. But I think there's a number of innovations that can make that happen. Yeah.
Anything to add?
But interested to hear from my fellow panelists.
I mean, I think in the ones there, it's nuclear power is so low emissions that probably even the existing fuel cycle, if probably is a net advantage. And I was thinking, we don't have to take any of our words. I'm sure it can be calculated. If you're just worried about the offhand effect of mining and so on, that's calculable. I'm things for sure. I would guess that it still wins.
Dr. Ledoux, we have a question here for you again. If the advanced reactors, if commercialized, could create multiple fuel types as compared to the current LWRs, are there prospects for fuel cycles that deal with this complexity efficiently?
That's a fantastic question. I think the verdict is out. I think that if you want to recycle into a fast reactor, as you cycle, I'm not a neutronics expert, but as you cycle, you do change the isotopics. And so it is it's a very important question of, as you go through it, until it reaches equilibrium, if you were closed, can a reactor live with that varying degrees? Can you blend it differently and so on? And I think all the AR companies considering that's an important question. Until it's demonstrated, I guess it can only be theoretically really analyzed at this point.
Appreciate that. Jon-Michael, we have a question for you now. Do you see any negatives for the new NRC approach on this EPZ process? And how will advanced reactors gain stakeholder approval or acceptance without involving them in emergency preparedness and response? I see this as being highly problematic for states and communities accustomed to the 10 and 50-mile EPZs. Thank you, Bridget Freimeyer, for that question.
That's an interesting and valid question. I don't see any problems necessarily with stakeholders. In fact, the reverse might be true. I think the very stringent prescriptive requirements that we have now, which require a very wide radius, may actually induce some kind of fear in people that's not necessarily warranted by the actual risk. And I think we have a lot of evidence to suggest that. But also in terms of stakeholder engagement, that's still required in the NRC's rulemaking process and in the process of reviewing applications. So there's still going to be a significant amount of public involvement. And that's actually, there's ongoing discussions about that in the policy world as well. So I think that's again a valid question, but I think that we can mitigate that and it might actually improve.
I appreciate that. Thank you. And that really mirrored a question that popped up in my mind in terms of how do we fill that niche? If our communities aren't engaged in that formal process, where do we need to replace it? So I appreciate that question, Bridget. Dr. Wise, I have a question for you specific about slide 8 on your presentation. I don't know if we can kick back to that slide while we're all talking.
I think I know which ones it is.
There it is. It talked about on that slide some new waste streams anticipated from advanced nuclear that are not yet well understood. Is it known yet what categories these waste streams could fit into? High-level waste, low-level radioactive waste, greater than Class C, et cetera. Is the concern that there is no disposal pathways for these? Do we just not know enough yet about the waste characteristics to know how to manage it?
Yeah, that's a really great question. A few things come to mind immediately. So the committee noted that without sort of more detailed design and operational information for some of these reactors, it's really hard to estimate specifically the type and amount and characteristics of some of the low-level waste streams, including potentially greater than Class C waste. And so rather than maybe going through all of these individually, I'll just recommend that if you're interested in this, to look in Chapter 5 of the report. I believe it's section 5.5 specifically, that has a sort of qualitative discussion about the different unique waste streams that might arise from advanced reactors. And then in terms of needing to learn more about these wastes, the committee did recommend that the implementer of the waste management and disposal program, I mentioned they asked Congress to establish this single mission entity. So that entity should collaborate with advanced reactor developers to do more R&D on understanding different degradation behavior of spent fuel from advanced reactors in different environments, and as well as on managing and disposing some of these unique waste streams. So hopefully that at least somewhat addresses the question.
I appreciate that, and thank you. I'll be adding section 5.5 specifically to my late night reading list, in addition to all the other good topics that y'all highlighted today. And there's a bevy of other good questions. I will recognize Elise Peterson, another colleague of mine from the state world of this industry from New York. Thank you for your questions, and I'm sorry that I didn't get a chance to pose them to any of the panelists, but I hope that you'll be able to connect with them after this presentation and follow up with them individually. And I will make just a couple closing remarks and thank everyone today. I want to thank you, Catherine, Robert, and Jon-Michael for your time today, and a special thank you to the DOE Office of Nuclear Energy for supporting this webinar. Reminder for everyone that registration is currently open for the NASCIO annual meeting in Portland, Oregon, October 16th through 19th, as well as the NARUC annual meeting taking place in La Quinta, California, scheduled November 12th through the 15th. You can find those registration links and agendas on the NASCIO and NARUC websites. And a reminder for ANSC members planning to join the facilitated discussion after this webinar, you should have received a Zoom meeting link to join that discussion in your inbox, and also received a calendar invite with the meeting invite earlier in the week. If you have any difficulty joining that facilitated discussion, please just email Kelsey or Catherine for that join link. They'll send it to you specifically. And a final reminder, for more information on other upcoming NARUC activities, just check the NARUC website. And I will conclude and say thank you so much. And Catherine, I turn it back to you.
Great. Thank you so much, Commissioner. And we will just end a couple of minutes early, but this was a phenomenal conversation, and we really appreciate all of our panelists here today. Thank you.
Thank you.